Hello everyone, I hope you are doing well. So in today's video, we'll be going through the 2021 physics exam short answer questions part 1, where we'll be going through questions 1 to 9. And so yeah, like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this video. Question 1. So two identical bar magnets of the same magnetic field strength are arranged at right angles to each other and are at the same direction from point P as shown in figure 1. Alright, at point P on figure 1, draw an arrow indicating the direction of the combined magnetic field of the two bar magnets. Alright, so to draw the overall combined magnetic field, so let's have a look at this North Pole here. First, let's look at this North Pole over here. Why is it very, let me just decrease my... There we go. So let's have a look at this North Pole. We know this North Pole, remember, arrows the magnetic field lines come out of the North Pole. So we'll have a magnetic field line coming out in the North Pole. And in the South Pole, in this case, the magnetic field lines are going to come into it. So imagine, overall, so you have a north here. Oops, let me rub this out. So you have a north, so an arrow going like this, and plus an arrow going like down. That's going to come into the South Pole over here. And so what we're going to do is we're going to add them. You're pretty much using addition of vectors, and that will give us our overall net. So when you add these two vectors, we're going to have overall a net, sum of magnetic field that is in this direction. And it does make sense because you got to remember it like this. So if you were like just drawing a normal magnetic field, these are going to just get attracted from north to south like that. And so if you look at the arrow, if you draw a tangent at this arrow, you'll see it's pretty much the same direction as what we got as our net. So overall, at point P, what you want to just draw is a arrow at it. So let's draw a nice arrow. Oh. Let's just draw a nice arrow that passes through like this. Beautiful. B, calculate the magnitude of the combined magnetic field strength of the two bar magnets if each bar magnet has a magnetic field strength of this at point P. Beautiful. So you know how we drew that triangle? So it was like this. Like this. Yep. All we got to do pretty much is, if we know that, the magnetic field that coming out of that North Pole was 10 milliteslas, and also from this one too, it's 10 milliteslas. All we want to do is we want to find the combined magnetic field, which is easy by using Pythagoras' theorem. Because we want it in milliteslas and everything's in milliteslas, I'm not going to convert them to teslas and just keep them in milliteslas. So using Pythagoras' theorem, so C squared equals A squared plus B squared. C is equal to, what's A squared? So pretty much 10 squared plus 10 squared. So using my calculator there, I should get... to how many significant figures? We want to 3 significant figures. We get 14.1 milliteslas. Beautiful. Question 2. A schematic side of view of one design of an audio loudspeaker is shown in figure 2. It uses a current carrying coil that interacts with permanent magnets to create sound by moving a cone in and out. Alright. And so here is what we're looking at. Figure 3 shows a schematic view of the loudspeaker from the position of the eye, shown in figure 2. The direction of the current is clockwise. Okay, they've shown that to us. Draw 4 magnetic field lines on figure 3, showing the direction of each field line using an arrow. Beautiful. So because we know this is the North Pole and the middle is the South Pole, we know that arrows come from the North Pole and go towards the South Pole. So we only need to draw at least 4. So I'm just going to draw 4. So north to south here. North to south here, and north to south here. And that's overall. I mean, you can draw more. It's at least, so they said at least, so you can draw, more, but I don't think you should. It's just a waste of time, to be honest. And yeah, so yeah, north to south, is that right? Yep, looks great. So B, which of the following gives the direction of the net force acting on a current carrying wire coil shown in figure 3? Alright, so when you're looking at something like this, we're going to use our right-hand slap rule, but you can pick any point on the graph. For example, if you're going to pick this point over here, the current is going down. In this case, it would be going down. Remember, if you're picking a point here, it's going to go to the left. This point going up, and this way is going to the right, as it's, in a clockwise direction. So we're going to use our right-hand slap rule. Make sure your thumb is in the direction of the current, which is to the right. Your fingers are going to go down to the direction of the magnetic field, and you should see your palm is going into the page. And so our actual force that's being produced is into the page. So choose E. Done. C. The current carrying wire has a radius of 5 centimeters. All right. So let me just rub this out. I don't need these anymore. So we know that this radius over here, the coil, this wire has 5 centimeters. That's your radius. So current carrying coil has a radius of this and 20 turns of wire. It carries a clockwise current of 2 amps. Its magnetic field strength is that. Calculate the magnetic force acting on the current carrying wire. All right, not too bad. So to do that, we need the length. Be careful. I think a lot of students will make that mistake of just writing 5 centimeters. Remember, this is your radius. We want that length of the total, circular coil, which you'll have to use, which is the circumference. The total length is the circumference. So to do that, we know to find the circumference of a circle, it's just 2 pi r, where r is your radius. In this case, it's 5 centimeters. Make sure it's in meters, so times 10 to the negative 2. That's going to give us a length, so I'm just going to write it actually as L. 2 pi times 5 times 10 to the negative 2. So that gives me 0.314 approximately meters. And so now we can use calculate our force. F equals N length times current times your magnetic field strength. So your N is the number of turns, which is in this case is 20. Your length of the wire, which we just got, was 0.314. Your current, they said it was 2 amps. And your magnetic field strength, which is 200 millitesla, so times 10 to the negative 3. Putting this in my calculator, I get to how many significant? To the lowest is 2, so I'm gonna 2.5. It's pretty much 2.5 newtons. Beautiful. Question 3. To calculate the mass of a distant pulsars, physicists use Newton's law of universal gravitation and the equations of circular motion. The planet Phobia orbits pulsar. So, all right, let me just draw this, just like a little diagram. So this is called this PSR. So pulsar is PSR. And so, sorry, no, that's PSI, yep. And so Phobia is orbiting, so that's the thing that's orbiting, so I'm going to call it just P. Orbits pulsar this at an orbital radius of this and a period of this. Oh, beautiful. Assume that Phobia follows a circular orbit. Calculate the mass of pulsar. So we want to calculate the mass of the central mass. So that's easy, using your Kepler's law in this case. So Kepler's law is r cubed over t squared is equal to gm over 4 pi squared. So we want to calculate m, the central mass, because we both have the orbital radius and the orbital period. And so that's going to be, rearranging it, it's going to be r cubed 4 pi squared over t squared times g, and that's going to be your mass. Is that right? Yep, looks good. So your mass is equal to r cubed. So what's your radius? We said it's 6.9 times 10 to the power of 10 cubed times 4 pi squared, all being divided by your period, which is 8.47 times 10 to the power of 6 squared, and g, which is 6.67 times 10 to the negative 11. And that's it. Let's put this in our calculator. No, in our calculator, 6.9 times 10 to the power of 10, power of 3, times 4 pi squared, 8.47 times 10 to the power 6 squared, times 6.67 times 10 to the negative 11. And so that gives me an overall, to how many significant figures? 2, the lowest is 2.7 times 10 to the power of 30 kilograms. Beautiful. Question 4. Liesel, a student of yoga, sits on the floor in a lotus pose as shown in figure 4. The action force so the force of gravity on Liesl is due to gravity is 500 newtons down. Identify and explain what the reaction force is to the action force shown in figure 4. Okay, this is pretty much an application of Newton's third law. So we know about Newton's third law. So let's write it down. I think you would want to write Newton's third law. So we know the formula for Newton's third law is pretty much just force on A by B. Let me write that nice. By B is equal to negative F on B, by A. This is a very simplified version of Newton's third law. So in this case, if I want to, and by the way, if you don't understand this, this is what it's saying. This is your action force, and this will be your reaction force, where reaction force is in the same magnitude, but in the opposite direction. So, for example, let's look at this case. So, using this notation, the action force, force of gravity, on Liesl, due to gravity. So, pretty much Liesl is our A value in this case, because it's on Liesl by B, which is gravity in this case. So, gravity is going to be B in this case. So, applying this formula to show the relationship, so we want to identify and explain what the reaction force is to the action force. So, we can write this formula. So, we now say force on A, which is in this case, what is it? It's Liesl. So, Liesl by gravity, which is remember, our action force. This is our action force. Acts downwards. We want to also kind of specify the direction. Yep. And so this is equal to negative F on switches around. So gravity. So on gravity by Liesl. And so this is your reaction force. And so this one acts upwards. Beautiful. And yep, so we've shown that negative. Yeah, that's just pretty much an application, a nice application of Newton's third law. So we've written Newton's third law. And so the force on Liesl by gravity is our action force, which acts downward. And your reaction force, which is the force on gravity by Liesl. And so this is our reaction, which acts upwards. And so, yeah, this is how I would do it. I think a lot of students will make this assumption, and it's a very stupid assumption. Don't do this in an exam. They believe that because, they may think that the reaction force is the normal force, which is wrong. The normal force is the surface acting up on you. It's the surface acting up on you. Be careful with that. That's wrong. So if it's Newton's third law, has to be an action-reaction pair. So that's if you're always confused, just make sure you use this formula. It's so useful. Just find your A and B and rewrite this formula, and it just gives you the answer quite nicely. And next question, 5. Figure 5 shows a stationary electron in a uniform magnetic field between two parallel plates. The plates are separated by a distance of this, and they are connected to a 200-volt power supply and a switch. Initially, the plates are uncharged. Assume that the gravitational effects on the electron are negligible. Okay, beautiful. A. Explain why the magnetic field does not exert a force on the electron, and justify your answer with appropriate formula. Well, quite easy. There is no velocity acting. Remember, let me write this down. So for a magnetic force to be produced, remember it's going to be QVB. This is a magnetic force formula, where you're going to need a velocity. In this case, we know that it's a stationary electron at the beginning. And so how is it, if your velocity is 0, how we're going to produce a magnetic force that's 0? So that's all. I think that's all we want to write in this case. So of course, your magnetic force, it doesn't exert because your magnetic force is 0 because our velocity is 0. So what you want to say, as velocity of electron is 0 meters per second, as it's stationary. Beautiful. Magnetic force, which is given by force equals QVB, is equal to 0 newtons. And that's pretty much it. Just be very precise in your answers, and So the switch is now closed. So now if you switch this close, we're gonna this is our positive supply, so this plate is gonna be positive. This is gonna be negative in here. So determine the magnitude and the direction of the electrical force acting, now acting on the electron. Show you're working out. So what do we know about electrical force? We know that electrical force, which is given by QE, and we need to find our, so pretty much we need to find our electrical field strength. And we also want the direction. So it's quite easy to determine the direction. Think about it. This is a negative electron, and so you have a negative plate at the top and a positive plate at the bottom. The negative electron is going to be straight away attracted to the positive plates, and it cannot even go up because remember, it will be repelled by those negative plates. Negatives both repel, so it's going to be pretty much going down. So your electrical force is going to go down. So you just want to write it down quite easy. And yeah, so let's use this formula. So if we need our electrical field strength. So to calculate our electrical field strength, we know that voltage is equal to ED. And so E is just voltage over distance. So we need to, we can calculate our electrical field by, what's our voltage, did they say? 200 volts divided by your distance. So separate, yep, so we're given the distance, which is 6.0 times 10 to the negative 3. Beautiful. Put this in my calculator. That gives me 333, pretty much 0.3, pretty much volts per meter. So we found our electrical field strength. And so putting this in your formula, remember it's an electron, so your charge is 1.6 times 10 to the negative 19 times 33333.3. So we get overall, how many significant figures do you want? Approximately 2. The loss we use is 2, so pretty much 5.3 times 10 to the power of negative 15 newtons. Beautiful. C. Ravi and Mia discuss what they think will happen regarding the size and the direction of the magnetic force on the electron after the switch is closed. So Ravi says that there will be a magnetic force of constant magnitude, but it will be continually changing direction. Mia says that there will be a constantly increasing magnetic force, but will be acting in the same direction. Evaluate the two statements, giving clear reasons for your answer. All right, let's look at again. Let's read Ravi's what Ravi's saying. So Ravi says that there will be a magnetic force of constant magnitude. Let's think about this. So we know that before the switch is closed. So when the switch, we know that the velocity is 0. In terms of magnetic force. So remember, magnetic force is QVB. So we know that before the switch was open, the velocity is 0. It was stationary, so the force is 0. And so when they turn on this, battery or, the switch, they turn up the switch, we're going to be producing an electrical field. And this electrical field is going to move this electron down. And it's going to start to have velocity. Its velocity is going to start increasing. And so when the velocity increases, your magnetic force increases too. So it will start from 0 and it will start increasing gradually. So is that what he was saying? Ravi says that there will be a magnetic force of constant magnitude. Nope, not constant magnitude. Remember, the velocity is increasing. It's increasing. So the force is changing. It's increasing too. It's not in a constant magnitude. So in terms of that, I'm going to just highlight it red. In this case, I'm just going to highlight that statement red. The next thing he says is, but it will be continually changing direction. Now that's true. It isn't a magnetic field, in a magnetic field, and now because it has velocity, it has a magnetic force, and so it will move because and we know that the magnetic force is going to be produced perpendicular to its velocity. So let's say in this case, the electron goes down, and so using your, because it's an electron, I'm going to use my left hand. So putting my fingers out the page and my thumb downwards, there'll be a force produced this way. So over a cause, remember, it's always perpendicular to the velocity. So the electron's going to move like this. It's not in a constant direction. It's changing. The direction is changing. And so that in terms of that statement, he actually got that right. But it will be continually changing direction. Yes, it will be continually changing. So I'm going to put a green part here. This guy really got that right there. So great. Mia says that there will be a constantly increasing magnetic force. Yes, we showed that. We've also showed that, so that's good. She said that right. But it will always be acting in the same direction. Wrong. We said that it will be continuously changing. So quite nice and easy. They both have something right and something wrong. And so now all we got to do is, I think, just write. So let me write these out and write my statement. So let's talk about Ravi first. So Ravi is incorrect to say the magnitude of the magnetic force is constant, but correct to say the direction is continually changing. Beautiful. Now let's talk about Mia. So Mia is correct to say the magnitude of the magnetic force is constantly increasing, so as she said, but incorrect. So Bash is incorrect to say it will always so what she says is always be acting in the same direction. Beautiful. And just a last statement where we just kind of prove what the true answers were and why what we said was true. So the magnetic force increases as velocity increases. As velocity increases by the magnetic field, by the electrical field that gives us the velocity. Yep, so the direction, now what we're talking about, continuously changes as the magnetic field, as the magnetic force is perpendicular to the velocity. And that is it. Beautiful. Question 6. Figure 6 shows a simple AC generator. A mechanical energy source rotates the loop smoothly at 50 revolutions per second. So that is our frequency. So we know our frequency is 50 revolutions per second, which is measured in hertz. And the loop generates an RMS voltage of 4.25 volts. The magnetic field B is constant and uniform, and the direction of rotation is shown as in figure B. So it's rotating clockwise. Sketch the output EMF between P and Q versus time on the grid below. Starting with the loop in the position as shown in figure 6, show at least 2 complete revolutions and include the maximum voltage of the vertical axis and the time scales on the horizontal axis. All right. I think a lot of students, be careful. I want to just tell you that whenever you're drawing an EMF over time graph, think of it as an oscilloscope. This here is the RMS voltage. You need to make sure it's a peak voltage peak when you're labeling it over here. So a lot of students, I think, make that mistake. So yep. So we just want to, before we start, I want to convert this to peak voltage. So remember, peak voltage peak is just the square root 2 of volt RMS. So just multiply that, 4.25 by root 2. And so we can get which is pretty much 6 volts. Our peak voltage is 6 volts. So I'm going to label that. So I think these are all the 6. So 1, 2, 3, 4, 6. So we have 6. And I'm going to just draw this. I'm going to just draw little lines that tell me where the number 6 is. So I'm going to say that's 6 volts here. 1, 2, 3, 4, 5, 6. Is it a... Yep, it looks good because they're using slip ring. So, yep, we're going to have an AC direction, AC current coming this way. So that's also negative 6 volt. Beautiful. So we've drawn that. And we can also find our period of the graph by... Remember, period is just 1 over the frequency. So 1 over 50. So 1 over 50, which is 0.02 seconds. All right, that's our period. And so when you're trying to draw an EMF, I always suggest that students should draw the magnetic flux over time graph, because that will be very helpful in determining the EMF graph. So let's do that. So what I'm going to do, draw a magnetic flux over time graph of pretty much the 2 loops. So, okay, we can see that the magnetic flux at time equals 0 when it starts is maximum, because the field lines are going into the plane of the loop. So it's going to start at the maximum value. And again, now all we got to do is it's going to rotate, and it's going to get, this is 1 rotation, and we want at least 2, so another 1 here. So that's 2 rotations. And so when you're drawing your EMF, you need to always just remember this. Whenever you have turning points, make sure they become our x-intercept. For example, this is a turning point, it'll be here. This here is a turning point, so it'll be, for our EMF, it'll be 0. This turning point will be 0, this will be 0, and this will be 0. So we already got some where it will cross the t values. And now, all we got to do is this. Remember, okay, let me write the formula. Negative n, and don't even worry about n, just your negative change in flux over time. This value here is our gradient. This value is our gradient of this graph over here. So think of it like this. Let me write that. So that's flux, that's time. So this is, this is our gradient. So let's say, for example, we wanted to draw this part over here. We can see that the gradient is negative as it's going down. So if this value is negative, it gets multiplied by a negative is negative, so it becomes positive. So when you're drawing your actual EMF, it's going to be a positive value. So, because, from here to here, it's all positive. So it's going to have, your EMF is going to be positive. It's going to be up here. It's going to look like that. And so from here to here, what am I doing? What? Yep. So from here to here, it's positive. You can see the gradient is positive because it's increasing. So when it's increasing, your gradient is positive, but remember, it gets multiplied by that negative. So it becomes negative overall. So it's going to be below. And so you can see that there's a sequence. So now it's going to go like that and that, pretty much. And that is how your EMF graph would look like. If you do methods, you are in luck, because you should realize that the blue graph is just it's your magnetic flux, which is in this case cos t. In this case, it's a cosine graph. It's a positive cosine graph. And so if we want to write this means you find derivative. So the derivative of that is what? So change in t over change in time is negative sine t. And so you multiply by negative, so it becomes positive sine t. A sine graph is pretty much what a the yellow graph looks like. So if you do methods, you would have straight away knew that. It's very helpful, yeah. But if you don't know, just do what I did. Just look at the gradient and make it, if it's positive, make it negative, yeah. So I know for a fact it's going to look like that. And so it's going to, each loop, so each, complete revolution has a period of 0.02. So I want to count these. Just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay, 30. So if they're 30, I want at least 2. So I'm going to do 6 in each. So I'm going to do 6. So for example, 12. So 1, 2, 3, 4, 5, 6. So that 1, 2, 3, 4, 5, 6. That's another one. So that's going to be a complete revolution here. And then you do it again. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And so that's going to be another revolution. And that's because it said at least you can draw an extra. So 1, 2, 3, 4, 5, 6. Beautiful. And so now let's draw what we drew in that yellow graph. So it's going to, halfway through, it's going to look like that. And so it's 1, 2, 3, like that. So I'm just going to draw. Looks like this. It's going to pass through here and it's going to go like that. Like that. Perfect. So then draw another one. It's going to pass nicely like that. Oops. Where's it? Where is it? Really struggling. Come on. Beautiful. Approximately like that. So if I move this like that. Beautiful. And so that's all I need to pretty much draw. I'm just going to duplicate this. So duplicate this to here. Is that right? Looks, yep, like that. And duplicate another one would be approximately here. So I'm going to take this, duplicate, and right over there. Done. So that's how the graph would look like. And remember, we also want to, so we've done the max of volta and the vertical axis. We want to put timescale. So this here, this is 1 complete revolution. So that's going to be 0 seconds. This is going to be 0.02 here. This here is going to be 0.04. And yeah, that's it. That's how your graph should look. A very nice detailed graph. B, describe the function of a slip rings is shown in figure 6. You should know this. These questions are so repeated in every exam. They'll always tell you two definitions normally. They'll tell you what's the definition of a slip ring or what's the definition of a split ring commutator. And you should always have these in your summary sheet. And yeah, don't even worry about struggling. Just make sure, look at your summary sheet. Make sure you have the definition in your summary sheets and sure to copy and paste them right in your exam. That is the main thing I always tell my students. And so, yeah, describe the function of a slip ring. I'm going to look at my summary sheet. I'm going to find where the definition is. Slip ring. Yep. So a slip ring, let me write it down because it's only one mark. This is beautiful. So it's a component. So it's a component used to maintain a constant electrical connection between a stationary external circuit. So circuit. Why do I struggle writing circuit? So circuit and a rotating coil and a rotating coil. Beautiful. How could the AC generator shown in figure 6 be changed to a DC generator? Very nice. So if you want to change an AC output to a DC output, you just have to, replace your, you need to just replace your slip rings with a split ring commutator because it's going to rectify those voltages and the current. So let's write that down. So we just want to say replace the slip rings with a split ring commutator. It's only 1 mark, so I think that's all you're going to need to write. You don't have to go in detail. Beautiful. I sketched the output versus time for the DC generator for at least 2 complete revolutions on the grid below. Include a time scale on the horizontal axis. No scale is required for the vertical axis. Pretty much, we know what happens when you replace a slip ring with a split ring commutator. It's just going to rectify these voltage over, the negative voltages over here would just be rectified, so they'll become like this. So in this case, I'm just going to copy this whole thing here. I'm just going to copy this whole thing. I'm going to copy and I'm going to paste it here, and I'm just going to just do some changes. Bring it right over there. Like there. Beautiful. So I'm going to rub these parts out. These, we won't have anything below. Nothing below. Let me rub those out. And so that looks good. They said we don't need to include any voltage. So it'll look something like that. And we already have the timescales. All we're going to do is I'm going to just replicate these. Duplicate this, put it right over there. Duplicate that, put it right there. And this is how your actual, in terms of, if you replace with a split ring commutator, this is how it should look. And so yeah, no scales required for the vertical axis, include timescales. Beautiful. The timescales are already there, so we don't have to worry about that. And yeah, it looks great. Beautiful. Question 7. The generator of an electrical power plant delivers 500 megawatts to an external transmission lines with an operating at 25 kilovolts. So I just want to draw a diagram. So I know we're producing, so this looks like an AC. So let me draw a diagram. So we're producing, a generator is producing 500 megawatts of power and at 225 kilovolts. The generator's voltage is stepped up to 500 kilovolts for transmission. So we're gonna have, it's being your voltage, it's being stepped up. So this is your step up transformer. So of course, so the generator's voltage stepped up to 500 kilovolts. So now 500 kilovolts for a transmission, and step down to 240 volts. All right, and so probably have an external, we'll probably have a transmission line 100 kilometers away. The overhead transmission lines have a total resistance of that. Assume, okay, yep, beautiful. So we have, this is a nice typical question. So, yep, this is 30 ohms. And remember, this is your transmission. And so we're going to also step it down for domestic use. I'm just going to draw a light globe, just thinking it like, yeah, I would like to draw a light globe showing that this is like, the domestic use there. So, yep. Yep, and so here is 240 volts, this said. Yeah, and all transformers ideal, so the power is not lost through the transformers. Explain why the voltage is stepped up for transmission along the overhead transmission line. Very, very beautiful, nice question. So why do we step up the voltage from 25 kilovolts to 500 kilovolts when we're in those transmission lines? It's because why? Let's explain. It's because when you step up your voltage, you decrease your current. So let's think about it. We know power here is going to be equal to the same power over here. So your input power is going to be equal to your output power, because there's no power loss in terms of these ideal transformers. And remember, power is voltage times current. And so if our power is, constant, and if we've increased this voltage, what happens to our current? P equals V. And so if our power is constant, but we increase our voltage, we decrease our current in those transmission lines. So we will actually have a low current in that transmission lines. And so why is that good? Well, let's think about it. We know that power loss is equal to I squared over R, where power is proportional to I squared. So if you have just a little bit of more current, it has a very significant power loss. So decreasing your current, decreases your power loss. Hence, overall, we step up the voltage because we want to decrease the current in those transmission lines, and hence we will decrease the power loss in those transmission lines. And so there will be more power for the other transformer, and for which again it's also ideal. And so your domestic use have as much power as they want. Not, at least it's not lost. That's the point. So yeah, explain why the voltage is stepped up. That's what we want to do. And yeah, make sure just be careful. The power is constant. A lot of people forget power is constant because, we don't lose any power to the transformer. And so now, let's just put these, let's write a statement that goes through all what we just said. So, power loss, which is P equals I squared over R, is directly proportional to current. So step up voltage leads to reduced current for the same power transmission. Hence, less power loss. Beautiful, because it's only 2 marks. We don't want to go into much detail. And I think that's all you need to say. One mark you'll get by saying that power loss is I squared over R and it's directly proportional to current. So stepping up voltage reduces current, and hence power loss is decreased for that same power transmission. Beautiful. B, calculate the current in the overhead transmission line. Show you're working out. So we want to calculate this current in this transmission line. And so if I know that the output voltage is 500 kilovolts, and because I know that 500 megawatts it's an IDC transformer, so this 500 megawatts will be the same over the output power in the transformer. So if I know that, I know to get the current, it's P equals VI, where I is just P over V. So what's our power? It's 500 megawatts. So 500 times 10 to the power of 6 to get what? Divided by the voltage, which is 500 kilovolts, which is times 10 to the power 3. So that's going to give me 1,000 amps. And because we want it in kiloamps, that's just going to be pretty much 1.0 kiloamps. Beautiful. Determine the maximum power available for the domestic use at 240 volts. Show you working out. So we're just saying what will be the leftover power for this domestic use over here. So let's think about it. We know that power through the step-up transformer here, that 500 megawatts is going to be the same in the output. But because there's going to be some at least power loss here, remember the current here at least is 1,000. Let's find the power loss that is lost to the transmission line. Power loss, which is I squared over R, is equal to 1,000 squared times your resistance, which is 30. Yep, 30. So this is how much we've lost. That's I'm gonna write 3.0 times 10 to the power of 1, 2, 3, 4, 5, 6, 7. 7 watts. I want to double check it. Is that right? 1, 2, 3, 4, 5, 6, 7. Yep, 7 watts. So that's how much power is lost to this transmission line. And so if we started with 500 megawatts over here, and we've lost some here, we've lost that much, how much would be left over here for this transmission? It would just be minusing your 500 times 10 to the power of 6 minus 3.0 times 10 to the power of 7. That's going to give me 4.7 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8. 8 watts. Let's double check. 1, 2, 3, 4. So 1, 2, so 1, 2, 3, 6, 7, 8. Yep, 8 watts. And so we got the power that will be received through the input voltage of this transformer. And because you remember it's ideal, the power will be the same over here. And so this is how much power that will be received by this 240 volt. This much. Because we want it in megawatts, just make sure you divide this by pretty much a million to get it in megawatts. Let's do that. 1, 2, 3. So, yep. So we get overall 470 megawatts. Beautiful. Question 8. On 30th July 2020, the National Aeronautics and Space Administration launched an Atlas rocket containing the Perseverance rover space capsule on a scientific mission to explore the geology and climate of Mars and search for signs of ancient microbial life. A liftoff from launch. The acceleration of the rocket was 7.2 meters per second squared. The total mass of the rocket and the capsule at launch was 531 tons. Calculate the magnitude and the direction of the thrust force on the rocket at launch. Take the gravitational field strength at the launch site to be 9.8. Give your answer in meganewtons. Show you working out. All right. So if we want the thrust, we know that the thrust force will be upwards, of course. That's where thrust is. So thrust, I'm going to write it as T. It's going to be acting upwards. And we're also going to have on this graph, a force of gravity on this, but it's going to be less, this force of gravity. We're going to, of course, have a force of gravity. So force of gravity that will be acting down on this rocket. And we know that the thrust is larger than the force of gravity because it will be accelerating upwards. Your acceleration should be upwards. So we're going to take your acceleration up. So our direction to be positive is up. So pretty much your F net, we can say F net, your overall net force is adding those two up. So it's going to be T minus your force of gravity, which is mg. Yep, minus means because, remember, we're taking up as positive, but because Fg is negative, we're going to have to make sure it's negative. Yep. So F net, again, is just, so we want T, which is thrust, so it's just going to be F net plus mg equals T. And F net's MV, no, MA, so mass times acceleration, plus mg equals t. So m we can take as a common factor, so a plus g equals t. So your mass, which is, what's a mass? It's 531 tons, which we have to multiply by 1,000 to get it in kilograms. And so your acceleration is 7.2 plus your g, which is 9.8. And overall, this should give you the thrust. And we also wanted to give the direction. Of course, thrust is going to be acting upwards from the diagram really up here. So let's calculate how much that is. 531 times 1,000. 7.2 plus 9.8. And so we also, yep, that will give me that. And I want to divide it by a million because I want it in meganewtons. 1, 2, 3. That gives me to, let's say, yep, 3 significant figures, 9.03 meganewtons. On 18th of February 2021, the Perseverance rover space capsule, traveling at 20,000 kilometers per hour, centered Mars' atmosphere at an altitude of 300 kilometers above the surface of Mars. The mass of the capsule was 1,000 kilograms. Calculate the kinetic energy of the capsule at this point. Show you working out. Beautiful. So we know kinetic energy is half mv squared. So we know the mass of the capsule, and we want the velocity, but be careful. The velocity is given in kilometers per hour. We want to make sure it's in meters per second. You should remember from unit 2 physics, that to convert kilometers per hour to meters per second, it's pretty much dividing it by 3.6. So if we want to go from kilometers per hour directly to meters per second, it's just pretty much dividing it by 3.6. So in this case, 20,000 divided by 3.6 is going to give me, wow, so 5555.55 meters per second. So putting this in my formula, half your mass, which is 1,000 kilograms of the capsule, times your velocity, so 5555.5 squared. That's going to give me so how many significant figures? 3 significant figures, pretty much 1.54 times 10 to the power of 3 joules. Beautiful. What do I mean power 3? Power of 10, sorry. 1.54 times 10 to the power of 10. What did I write here? Yep. And so figure 8 shows the gravitational field strength of Mars versus altitude, all right? So this is at the surface of Mars. Calculate the gravitational potential energy of the capsule relative to the surface of Mars at an altitude of 300 kilometers per hour. Kilometers. So saying from the surface, which is over here, to 300 kilometers, which is halfway through here. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's just halfway is 5. 1, 2, 3, 4, 5. So here is 300 kilometers. So put that upwards. Beautiful. And so it's an actual trapezium. So this is our trapezium formula to calculate the area. So that. Yep. And that. So your height is this. This is your A. And this from here to here is your B. So area over trapezium is half, which is A plus B times height, which is half your A in this case, which is where does it go by? 2, 4, 6, 8, 10. Okay, so it goes, so it's 3.2 plus B, which is 2, 4, 6, 3.7. Times your height, which is 300 times 10 to the power of 3. Make sure it's in kilometers. We want to make sure it's in meters. And so this here will overall give me the area. And because, be careful, a lot of students will make this mistake. They think that area straight away is your energy. Now that's false, because remember, it's an actual G value. It's gravitational field strength versus a distance graph. And so when you find the area, you just have at the end you just have to multiply by the mass of the capsule in this case. So if I want, for example, energy, all I have to do at the end is just multiply by 1,000, which is the mass of the capsule. Yep, is that the, yep, yeah, it's 1,000 kilograms. Beautiful. Power 3 times 1,000. So that gives me, how many significant figures? Let's say so there's 3. So 1.04 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 joules. Beautiful. D. The capsule used in aerodynamic braking as it descended from Mars' atmosphere to reduce its speed from 20,000 kilometers per hour to 1,600 kilometers per hour. The capsule was then at an altitude of 10 kilometers above the surface of Mars and had 1% of its original combined gravitational potential energy and kinetic energy remaining. Describe how the 99% of the gravitational potential energy and the kinetic energy of the capsule was first transformed and dissipated as the capsule descended from an altitude of 300 kilometers above the surface to an altitude of 10 kilometers above the surface. No calculations are required. So let's have a pretty much basic analysis of what's happening here. So, say this is your Mars in this case. Say this is your Mars. And say this is your capsule. And say it's at a distance right now of, 300 kilometers above the surface. Now, the thing is, because it has a very large, height, the difference between, it has a very large, your radius is very high, it means that the gravitational potential energy here is very high, and your kinetic energy is very low. And remember, the sum of these have to be constant, because the total energy is always constant. And so, as the, in this case, what is it? Is it a spaceship again? Or the rover, what is it? Oh my God, capsule. As the capsule goes down to like 10 kilometers per hour above the surface, what has happened? Your gravitational potential would have decreased. And so your potential, and what would have happened to your kinetic energy? It would have had to increase, because remember, both have to be constant still. So overall, when the capsule goes down, we know that the gravitational potential energy decreased. It transformed to kinetic energy as it went down, as the total energy is constant. So now let's talk about in terms of the atmosphere and the aerodynamic braking. So let's think about aerodynamic braking. Now, if you don't know what aerodynamic braking, think of it like if you haven't watched movies like Interstellar or something like that. It's like when you have, imagine a meteorite just falling towards the earth, and you know how it's like fiery. It's fiery. It has a lot of resistance. And we're gonna explain what's happening. So that kinetic energy that was that gravitation, as we knew that gravitational potential energy transfer all to some kinetic energy. As it goes towards our atmosphere, what's really happening? There's gonna be some energy that's dissipated, especially the kinetic energy. So the kinetic energy actually changes, and so your kinetic energy changes to many forms, like for example heat. So as the capsule falls, as the capsule falls, we're gonna get heat because of the friction of the atmosphere. There's a lot of friction the atmosphere gives, so there's gonna be very much heat. So some of the energy becomes heat. In this case, it will also have sound, light, because it's very it has a very high light. So energy would have been heat, sound, light, and also friction due to gravity, and that's friction due to atmosphere, and pretty much that's all I know. I mean, that's all I think you should write in terms of this. So we did talk about what happened to the energy, because we knew that the kinetic energy increased as the potential energy decreased. And how it was dissipated pretty much by aerodynamic braking. So as most of that kinetic energy then transformed to heat, sound, light, and friction. So yeah, I think that's all you're going to need to write in this case. So let's write, what are we saying? We're going to say the capsule's kinetic energy increases and its potential energy, not potential, be careful, just make sure you write gravitational potential specifically. Gravitational potential energy decreases by equal amounts as it descends, as the total energy is constant. Beautiful. So with the atmosphere, with the atmosphere, aerodynamic braking, aerodynamic braking changes the kinetic energy. Remember, it's specifically kinetic energy because remember that friction and stuff. The velocity, as you know, we might think that the velocity is increasing because all of that gravitational potential energy had transformed, but because the atmosphere is pushing due to friction, it's that velocity is decreasing. So hence all that kinetic energy is being transformed to something. So that's what we're talking about. So aerodynamic braking changes the kinetic energy to many energy forms, etc, etc. We said heat, sound, light, friction due to gravity also, and due to gravity. These are all the kind of forms that kinetic energy pretty much dissipated to, in other words. And I think friction due to what? Gravity, atmosphere. Sorry, not gravity, atmosphere. Beautiful. I hope that's right. A nice right statement. Question 9. So the last question. Abby and Brian are about to go on the first loop-to-loop roller coaster ride. As competent physics students, they are working out if they will have enough speed at the top of the loop to remain in contact with the track while they are upside down at point C. Shows in figure 9 the radius of the loop CB is R. All right, beautiful. The highest point of the roller coaster at point A, is 15 meters above the point B, and the car starts at rest at point A. Beautiful. So pretty much, if it starts at rest, there's no kinetic energy, so your kinetic energy here is 0. And your gravitational potential energy is at its maximum value. Assume that there's negligible friction between the car and the track. What is the speed of the car at point B at the bottom of the loop? So at the bottom of the loop, we know that the gravitational potential energy is 0. And so the kinetic energy must be at its maximum value because remember, your total energy, which is adding these two, must equal to a constant value. And so adding these two must also equal to that constant value. So all we got to do is make this equal to your kinetic energy. So mgh is equal to half mv squared. So the m's cancel out, so it's just gh half v squared. So which is just the square root of 2gh is your velocity. So your velocity here is pretty much 2. G is 9.8. And your height in this case, which is 15 meters. Beautiful. That's going to give me pretty much, how many second figures would we say? 17. 2. So 17 pretty much. So 17 meters per second. Beautiful. By considering the forces acting on the car, show that the condition for the car to just remain in contact with the track at point C is given by this. So for it just to remain in contact, we know that the normal reaction force must be 0 at point C. So remember what other forces acting? Of course, we're going to have a force of gravity. Of course, we're going to normally have a normal reaction force that always acts downwards too here. So if we write those down, F net, so to N plus mg in this case. So N is equal to 0 for the car to just remain contact. To just remain in contact with the track. Beautiful. Done. So if n is 0, so F net, which is pretty much F net's mv squared over r anyway. So mv squared over r, n0, so it's mg. The m's cancel out, which is v squared over r, which is equal to g, and we have proved the formula. Beautiful. C, what is the maximum height of the loop x meters? So we want to calculate x, so which is, let me rub all this. This is kind of confusing. It's too much stuff. Let me just rub these out. So x is the overall diameter of the circle. What is the maximum height of the loop x meters that will ensure that the car stays in contact with the track at point C? So we're going to be using this pretty much, this formula over here still, because it's still just remaining in contact with point C. All right, so let's think at point C. I'm going to use energy transformations because if I know that overall here, it's just gravitational potential energy, and at this point, of course, there's both gravitational potential energy and kinetic energy. So if I equate these, so we know that mgh is equal to mgh plus half mv squared. So mgh is from this one, and mgh plus half mv squared comes from this, and they must equate because the total energy must be a constant value. So the m's cancel out, so it's just gh equals gh plus half v squared. This h in this case is 15, because so that's 15. This h here is the height of this here, which is x meters. I'm going to write, so gx, oh, not that one, what am I writing? So here, sorry, gx plus half velocity squared. So this is the velocity at point here, where it just remains in contact, and we just calculated that. We know that v squared over r is that, so your v squared is just rg. So we can actually just replace that v squared with rg. Oh, oops, rg. Done. The radius, by the way, the radius of this is just half of x. So we can replace that r with x over 2. So let me write, so that's going to be like g here and x over 2. All right, and so let's simplify this. So we pretty much made a nice equation that relates all of these. The g's cancel out because all of them have g, so it's just going to be 15x plus x over 4. X times x over 4, which is 15. So x plus x over 4, which is 5x over 4. So x, in this case, 15 times 4 divided that by 5 gives me x is actually equal to 12 meters. Beautiful. So x, the diameter is, overall, this diameter is 12 meters. Beautiful. Oops, what am I doing? 12 meters. Done. D, if the friction is taken into account, will Abby and Brian need to increase or decrease the predicted value for the radius of the loop? So, all right, we know that for it just to remain in contact, we know that velocity is just the square root of rg, pretty much. That's what we know. And so, if friction was taken into account, the velocity decreases. This is because when there's friction, the kinetic energy decreases. The kinetic energy decreases, hence your velocity decreases. So if your velocity decreases, your radius must also decrease, because it's actually proportional. Your velocity is proportional to the square root of r. So whatever happens to the velocity happens to your radius. So for Abby and Brian to not fall down and for them to still be on the track, staying in contact with the track, the radius must also decrease. If their velocity overall decreases, their radius must also decrease. So let's write that down nicely for 3 marks. Wow. So the radius must decrease, as we said was velocity is equal to the square root of rg. We know that velocity will decrease due to friction, which kinetic energy gets converted to heat, pretty much. When there's friction, gets converted to friction. Yep, gets converted to heat. And so velocity is less. And as v, so velocity is proportional to the square root of r, the radius must decrease. The radius must decrease. And beautiful. And I think that is it to get full marks. And that's the end of this exam. Not the end of the exam, but end of half of this short answer questions. I hope you guys enjoyed this video. If you guys want the next part, I am going to try to upload that in hopefully the time being. I hope you guys enjoyed this video. Please make sure to like and subscribe and send this video to your friends to help them out. I hope this video finds you well and helps you a lot in terms of physics studies. And yeah, make sure you guys have a great day and take care of yourselves. Bye-bye.